Hey everyone, we'll get started with our next talks. It's Pandas and Dask DataFrame 2.0, comparison to Spark, DuckDB, and Polars. So we have Patrick. Please give him a round of applause. The talk is from 2:30 to 3. We have 5 minutes of Q&A at the end. So if anyone has questions, we have 2 mics over there. Feel free to come over and ask any questions that you have. Over to you, Patrick.
Thank you for the welcome. I'm here to talk about Pandas and Dask DataFrames today and how we improved them over the last 12 to 18 months, and how they now stack up mostly to Spark, but we'll also focus a little bit on DuckDB and Polars later. My tagline is for how Dask is actually pretty fast now. Historically, users of Dask might know that Dask wasn't always fast or easy to use or generally pleasant. All of that changed. So briefly, a couple of sentences about me. I work for Coiled, where we focus on deploying Dask clusters for our customers and also improving Dask generally, like the open source library. I'm a Pandas and Dask maintainer. I've worked on Pandas way longer than I have been at Coiled, and that's where I originated from. I'm settled into the DataFrame world. Dask itself is a distributed computing library, and it integrates with the whole PyData stack. There aren't many libraries that don't have a Dask integration in some way. So if you hit scale limits or need better performance or whatever, Dask is probably able to help you. Today we will focus on 3 different things. We will spend the first half of the talk on Dask DataFrame improvements, how Pandas 2.0 helped with that, and what the current status is. Then the second half will be focused on the benchmarks we ran and how Dask stacks up compared to Spark, DuckDB, and Polars. And then we'll have a brief view ahead of what we are intending to do over the coming months for Dask DataFrames to make them even faster. The first part is mostly separated into 3 different topics. Shuffling, which means network communication. Strings. This is probably familiar to Pandas users and Dask DataFrame users that they kind of sucked in the past. And how we added query planning to Dask, which wasn't available before. This is the bigger part of the talk because this is just a broader topic to cover. Pandas historically used NumPy object to represent strings, which is slow, memory intense, and just not very pleasant to work with. But for a couple of years now, there's an arrow integration in Pandas available that enables a lot easier to use string interface, and that's also more efficient. I call them PyArrow-backed strings. It's basically the arrow memory layout that is used to represent strings in memory. They have 2 very clear-cut improvements over object data type. We've run some quick benchmarks because the advantages are relatively obvious. They are a lot faster, 2-3x on Pandas, and for Dask they are even better because they don't block the GIL, so they enable multi-threading better, which can give us up to 10x improvements compared to if you do a lot of string operations on NumPy object. Even more important for distributed workloads is they are often constrained by memory. We looked at one of our demo data sets that we use to show how you can work with Dask. That's a table that has a couple of billion rows, nothing too large for Dask, and 20 columns, 2 of them are strings. Memory usage originally was 220 gigabytes, and then converting these 2 strings to arrow strings cut us down to 90 gigabytes, approximately. So if you have 20 string columns instead of 2, then you get even more improvements. Roughly, I would expect this to cut memory usage by 60 to 70% on an average data frame. That's not only numeric, obviously. This was one of the first improvements we did. It was relatively clear-cut. There wasn't much complication. It was just swapping NumPy object with arrow strings. It was a little bit more complex than that. The second thing we added is a new shuffle algorithm. Shuffling in distributed system means that all workers have to communicate data to each other. In-memory transformations normally run with like 5 gigabytes per second. If you send stuff over the network, depends a little bit on the network connection, but normally it's a couple hundred megabytes. So it's up to a factor of 50 faster to do in-memory stuff. Even if you could make Pandas like 10 times faster, that wouldn't matter much to us. Improving the bottom legs, which is I/O and network communication, is way more important for any distributed workload than getting the last 2% out of in-memory transformations. Historically, Dask used a shuffle algorithm that didn't scale linearly with the dataset size. It scaled log n times n, which is, I guess, pretty bad. A complete rewrite, we call this P2P because the workers communicate directly with each other, and reduce this to linear scaling. So if you double the dataset size, this will also roughly double the amount of work that the cluster has to do, which is just a lot more reliable. Even if we ignore performance completely, Dask didn't scale very well in the past. This is now all in the past. You can just double, triple, 10x increase the data sets, doesn't really matter, and the shuffle will just run smoothly. This is like a quick illustration. We could talk for 2 hours how we improve the shuffle algorithm. This is not really the focus of this talk. In essence, we replaced this middle layer that scaled with log n times n with one single task. And so we hid everything away from the system, making it a lot faster and more resilient. Another cool thing is, historically, Dask used a shuffle approach that kept everything in memory. So if you were merging like 2 huge tables, at some point, all of that would have to be in memory. Now we use the disk a lot more efficiently if necessary, which means that you can shuffle arbitrary large data sets by constant memory. It doesn't really matter anymore, as long as your VMs have enough disk. This is something we've ran into with a couple of benchmarks. The third and proportionally also the biggest improvement is that we added query planning to Dask DataFrames. Users that have used Spark or SQL databases already know this. The query is like optimized a lot before anything is actually run. This wasn't something that Dask did historically. It just took what you gave it and executed it like a dumb little monkey, basically. Our optimizer isn't very advanced yet. It just does a bunch of things that are clear and obvious wins. We didn't want to make stuff worse for anyone, so we only added stuff for now that makes everyone's lives better, basically. Column projection and predicate pushdown is one of the techniques that is like general purpose. This is not only relevant for distributed systems, this also helps like single node systems like DuckDB, Polars. Theoretically, this would also help Pandas, but there are a couple of other hurdles to clear before that. We have a query here. It reads 2 data sets, merges them together, and in the end, we only care about like 2 columns, customer key and order total. Historically, Dask would have read everything, even if your data set has like hundreds of columns, and you only need one of them. Just get all of them from S3. It's cheap, you know. This translates roughly in a graph that looks like this. We have this read parquet, these 2 read parquet tasks, then we have a join that shuffles. Remember, we read all columns and then send all of them over the network. There's not much that can go wrong, obviously. And then we did a filter, which potentially reduces to like a single row. We don't know. And in the end, we pick 2 columns that we actually care about. The query optimizer, like very shortly summarized, does the following. It looks at the query and identifies that the filter happens right in the end. This is not very efficient. We could do this earlier. So it changes the order of the shuffle and the filter. And it will also, like in practice, push this all the way into the I/O step. So maybe we can even avoid reading complete files from S3, which is not too bad. The group by aggregation in the end is basically a projection. It restricts the number of columns that we actually care about. So what the optimizer does, it identifies that actually only like 2 columns are needed in the end. So it will look how much it can push this closer to the data source. So we definitely don't need them in the join. So we can just pull the projection before that. And the filter also doesn't really need that. So we can immediately do this in the I/O step, which means that we only have to read like 2 columns on the left side and 1 column on the right side, which might be a 5, 10, 100, 1000x improvement. It really depends on the structure of your data. But generally, like, doing less work is always a good thing. It's like, I haven't run into any scenarios where doing less work actually resulted in a worse runtime. The second 2 things that I want to go into, like, the optimizer does like 10 different things, but only a couple of them are really game changers. The others are just small improvements here and there. A Dask DataFrame is a data frame that consists of many, many small Pandas data frames. If your Pandas data frames are like tiny, meaning only a couple of rows, then Dask will have a lot of overhead managing those. Having like a very good distribution of Pandas data frames, we generally recommend like 500 megabyte in memory. It's just more healthy for a Dask cluster, especially if you want to have thousands of workers. Having tiny Pandas data frames will then completely screw your system. So what we do now is we look at the Parquet files or any other file type that you want to read and check how big they actually are. If your Parquet file is only like 50 megabytes in memory, then we would take multiple of them and squash them together so that we keep a like healthy partition size. Also, if you only select a subset of columns, maybe 2 out of 4 or something like that, then we will look at the memory proportions from the columns that you read compared to the whole file, and then squash stuff together so that we just get a reduced partition count. Less partitions are normally good if they are not too big. Like if you have a Pandas data frame with like 5 gigabyte, then that's probably not healthy, but like a couple hundred megabytes is generally a good thing. Initially, when we did benchmarking, like you see the final results a little bit later, our results were kind of okay, but not great. And then we added this change for Parquet files specifically, and we got a 3x improvement with a 5-line code change. I wish there were more of that, but I don't think so. That was unfortunately a one-time occurrence. Another thing is like merge operations. Merges in the past always required an all-to-all network transfer. So we send all the data over the network. Even if you have a query chain that merges over the same column over and over again, we would still trigger a shuffle for every merge. So we have a query here that just merges 3 different tables. We merge the first one on a column X and the second one on the same column. So what Dask did historically, it did a shuffle join, which sends data over the network, and then it did another shuffle join, sending data over the network again. Even though like the data was already shuffled on the left side, so that really wasn't necessary anymore. We just did shuffles because, I don't know, maybe we liked them in the past. So what the query optimizer now does, it looks at this query and figures out that the second shuffle is pretty dumb. So we split the lower join into a trivial join, which is if you just do Pandas joins on the hood, and only shuffle the right side. So in the end, we can like save 1 shuffle. Depending on the dataset size, this might be a like 50% increase in runtime. We had queries in our benchmarks where we had like 5 subsequent shuffles all on the same column, and now like Dask is only shuffling once, and the query got like 4x faster, which is nice, you know. Summarizing, all these improvements like went towards the goal of making Dask faster, so that it was just like not slow as fuck. But a couple of side effects of this were, especially stuff like auto repartitioning and trivial merges, made it also a lot easier to use. Theoretically, users could have like performed trivial merges in the past as well, but that needed a lot of internal knowledge about how Dask works, and the optimizer now does everything out of the box. And we can also pretty much scale a lot more than we could previously. This is like a chart I like to show. If you've stepped by our booth, then you've probably already seen that. Like the left bar was probably in February last year, and then we activated all these improvements step by step. And now we are down here, which is in total like a 19x increase in performance. Granted, this was a query that is written down pretty dumb without doing any manual filter reordering or dropping columns when you don't need them anymore. We just wrote it down like you would it in SQL, basically. We went from like 950 seconds, which is quite a long time. This was 1 terabyte of data. You shouldn't need like 15 minutes to process 1 terabyte. That's not necessary at all, no matter what you do. Down to 50 seconds. So like reiterating on your development got a lot faster. This is pretty much the summary. This is probably the part why all of you came here. Now we look into benchmarks and how the like new Dask DataFrame compares with Spark, DuckDB, and Polars. I assume that most of you know all of these tools. Like Spark is a distributed computing framework that has been around the longest. DuckDB and Polars are both newer implementations that are a couple of years old that specialize on single node applications, and they want to push like performance on one machine as far as possible. This is why we thought that that comparison made sense. Why move to a distributed system if you can get the same performance on one node and you don't have to deal with all the shit that comes along with like network and whatever. We use TPCH style benchmarks. This is a benchmark set that is commonly used in data warehouse benchmarkings. We have a variety of scale, like we start with 100 gigabyte and we moved over to 1 terabyte and 10 terabytes. And as I said, like DuckDB and Polars run on a single VM, so they just get a huge machine that we rented on AWS. And Dask and Spark will get the same number of cores, the same memory, but they get a lot more machines that are just all smaller. This also correlates a lot to how these tools are used in the wild, so we wanted to make this as realistic as possible. The thing you have to know about TPCH-style benchmarks is that they reduce a lot. Sometimes, when you go through the query, you end up with a single number, and you started with like 10 terabyte of data. So this is not like comparable to feature engineering, for example, where you keep adding columns, and your memory probably like increases over the lifetime of your query. It goes exactly the other way. When I wrote the proposal, we didn't actually do any benchmarks, so I optimistically wrote like DuckDB and Polars on there. What we found out is that Polars isn't quite ready yet to scale above a certain scale, so this is why we focus on Polars only on the 100 gigabyte scale. DuckDB and Spark will then be part of the 1 terabyte and 10 terabyte scale as well. Sorry, this is a little bit confusing. We go over this real quick. The other plots are a lot more intuitive to read. This is like 100 gigabytes with 256 gigabytes of memory, so everything should fit comfortably, even if you load everything at once. And then what we can see is that there is not really a clear winner. Some tools are faster than others on some queries, and on other queries it's the other way around. If I would have to pick a winner here, it's probably DuckDB. They outperform Dask on most of the queries. Spark is just not quite good on that scale. They become a little bit better on bigger scales. And Polars that's what I meant with they have still some work left to do. Like, they're also the youngest tool, so they will probably get there. They struggle on the more complex queries. Like 18 that's something we'll see later. A query that's all systems struggle on larger scale. So they just had a little bit of problems there. But nothing that's impossible to fix with their architecture. Now we look at 1 terabyte and 10 terabyte. Like from a distributed point of view, this is where it gets interesting. Like 100 gigs is for Dask pretty small, also for Spark. 1 terabyte and 10 terabyte is where things get interesting, and then scaling out even further is the actual goal. We start with Dask versus DuckDB. Again, DuckDB runs on a single, very large VM. Dask runs just on many small VMs. But we get the same number of cores and the same memory. On 1 terabyte, what we can see immediately is that DuckDB is pretty fast. Again, it's an application design that's designed for a single machine. Them processing 1 terabyte of data in that time frame is pretty impressive. But they started to struggle a little bit. They were way more competitive on 100 gigs with the more complex queries, like 3, 6, 7, and 18 are the queries that are the most complex in this benchmark set. Dask is generally like, it's doing quite okay. It's not great. DuckDB is still outperforming us in some queries. We are hopeful that we can fix this at some point. But we are competitive now. If you go back a little bit, earlier I showed you the screen that we got 20 times faster over the last year. This was specifically on query 3 here. If you multiply the Dask runtime by like 20, then DuckDB would surprisingly be like 6 times faster than we are. Doing this for all queries would like make us stink pretty heavily. On 10 terabytes, DuckDB is still surprisingly competitive, to be honest. I didn't expect that. I did expect them to fail scaling out further, like after a couple of terabytes. The queries that they complete, they do this surprisingly fast. Like especially on like query 2 and query 8, they really kick our ass. They are like 80% faster than we are. But what you can see here is like the more complex queries are queries where DuckDB just failed. This wasn't timeout. They ran into some memory allocation issues because at some point they had to load everything into memory, and loading 10 terabyte on a 500 gigabyte VM is not something that will succeed. So the takeaway from this slide is basically like DuckDB is still surprisingly good if you have a workload that actually fits their paradigm. But if you have to scale out, then Dask is a better choice here. It's also like these queries took pretty long. Like query 3, for example, ran over 10 minutes. And at some point you'll hit a limit with DuckDB because there are only VMs that are so big that you can rent on AWS. But you can just use 100 more machines with Dask, and then you get a pretty impressive speed up. So if you actually need performance on that scale, like a distributed system is probably the better choice. If your query is sufficiently complex. Now we come to the more interesting part. This was the part I was looking forward to when we started doing benchmarks. Spark historically outperformed Dask on most benchmarks that I've seen. Like, Dask was just pretty dumb, to be honest. Like, it did work that it didn't need to. It also shuffling and stuff like that didn't really work very well. Spark was just better there. Which is why this makes me happy. We now outperform Spark on most queries on the 1 terabyte scale. There are still a couple of queries where Spark is faster. This is mostly driven by overhead, though, that we can hopefully address. That happens when we submit a computation to the Dask cluster. It's not actually in memory performance. Again, if we look back at like my previous slide where Dask now got like 20 times faster, a year ago you wouldn't even have started doing this because like Spark would have kicked our ass so heavily on query 1 alone that the other queries all wouldn't have been interesting. But when we move on to like 10 terabytes, this is why they are on a different slide. Sorry about that. Initially we tried running Spark on 500 gigabyte of RAM just to see how Spark, DuckDB, and Dask all compare with each other. This didn't go very well. Spark struggled heavily with heavy out-of-core processing. They weren't even able to complete query 1, which is basically just a group by and then a sum aggregation. So this is where distributed systems are helpful. We just increased memory by 10x. Which made Spark run a little bit more reliable, but also not very good. Dask is still fast on most queries, but the overhead hits us in the back half like pretty hard. On query 15, Dask has like 50% overhead. The actual query runtime is only 50% of the whole time. This is something that's fortunately pretty easy to fix. So I expect like that we have fixes for this in the next couple of weeks. The thing that surprised us a little bit is that Spark still failed on a bunch of queries. We couldn't really figure out what we were supposed to be doing differently. Like we asked the Spark expert who looks at Spark workloads every day, and he also didn't really know what is going on there. Our suggestion is that this is based on how Spark repartitions the data. We tried this on Databricks as well. A couple of those queries actually completed there, but you need a lot of time. Like they ran like 45 minutes, some of them. But probably half of them, I don't have an exact count in my head right now, also failed on Databricks. So this is just something that Spark seems to struggle with. We also increased like the memory further, and then it took a while, but it completed a bunch of those. But this is like a little bit odd. Like you actually needed more memory than the data set was big, which is like not really what this is supposed to be. The takeaways are, like DuckDB performs actually pretty well, especially since it's optimized for a single machine. It only started to struggle on 10 terabytes with the queries that don't drop as much data in the beginning. So if you keep a lot of data around, then DuckDB will struggle at some point. But if you're in the like couple of 100 gigabytes space, then DuckDB is a pretty good choice if you have access to big enough machines. Spark seems to be reasonably fast, but it needs a lot of resources to complete anything. Again, Dask could process most 10 terabyte queries with 500 gigs of RAM. Spark didn't even get one done. Dask is pretty competitive. This makes me like happy. But there's also a lot of room for improvement in the future. So I expect that we see another 2x improvement overall queries at some point over the next couple of months. And this is also what ties into my what's to come story. The things that we saw in those queries is like the up to 50% overhead that I already mentioned. And this is something that is like in 2 or 3 places where we have paper cuts that just cost us a lot on the 10 terabyte scale. But this should be relatively easy to address. Shuffle, while better, is still comparatively slow compared to everything else that's going on in these benchmarks. We currently have a like draft PR that's not quite ready to be merged. It gives us like 25 to 30% improvement over all queries. Like we probably make Shuffle like 3 times faster, which means that we get a 30% increase performance improvement for all queries total runtime. And the third point is like our query optimizer, as I said initially, is still doing pretty simple stuff. That's always better. There's a lot of room left for improvement where we can, on some queries, not overall, but get a huge performance improvement if you're a little bit more intelligent, when to shuffle, when to avoid that, stuff like this. So this is everything. Now we have a couple of minutes left for Q&A. Yeah? No, you were raising your hand. Some of the things, like the order repartitioning, is like specific to Dask because we know how Dask behaves internally. And for like query reordering, like joins and stuff like this, we looked mostly at DuckDB and Spark to see what they are doing and see if we can learn something from them. Any other questions? I'm sorry, I can't see very well. The lights are pretty bright. Yes? Not all of them. Like some things, if you have to actually inspect the data to know what to do, are hard in a distributed setting. I would put the coverage at like 90 to 95%. Okay, if there aren't any other questions, then we can close this. I am happy to be around if anyone has like, oh, sorry.
Sorry.
Yes? Generally, I would say to switch over as soon as like it gets annoyingly slow or doesn't fit into memory anymore. For Spark, it's probably a little bit trickier because they struggle on smaller scale a lot. They are just not very performant, so the barrier is probably higher there. Does this help?
One question. Did you see any cases where Dask failed to complete the queries?
We had one of those on the 500 gigabyte cluster for 10 terabytes. We struggled with query 5 there, which is a very, very join heavy. Like I think it's 5 joins after another. But this is the only query where Dask wasn't able to compute as the only tool. query 18 failed for both DuckDB and Dask on the 500 gigs cluster, but Dask was able to complete this after we increased the resources.
Thanks.
Okay, thank you very much.